Okay, good afternoon, class. Alright, let's continue on the topic of mapping here. Okay, so we started the mapping already from previous lecture, and here is just a quick recap. This picture here shows you basically system response corresponding to different locations of poles. Okay? For poles, this is a continuous system. Okay, this is a continuous in the continuous domain. So what we wanted to do is we want to recycle the knowledge we learned in the continuous domain, and we wanted to basically find out a similar type of a graph like this, but which is for the digital domain, basically. Okay, yeah. In the previous lecture, I have started essentially just sort of a preamble here as to what do we mean by mapping. Yeah. Bottom line is you have this expression here relating the S and the Z. So this relationship comes from the mathematical derivation when you apply an impulse sampling basically to a continuous signal, okay, then to transform from the Laplace transform to star Laplace, and then from star Laplace to Z, and you have this equality there, right? You know, basically to relate S and Z. So there are many examples. You know, you can literally see the basically the relationship showing up. For example, if I have a Laplace transformation, which is 1 over S plus B, and this is corresponding to exponential function, time function, and if you let it pass through this impulse sampling, then you get a discrete time signal, and this can be rewritten as this expression right here, and the corresponding Z transformation is this one here. So as you can see, basically here is S equal to negative B, and here you're in the discrete domain. Your pole is e to the power negative bt. So that's basically this relationship. Right, that's basically this relationship. Okay, yeah. This is basically when you have a real pole set here, right? This real pole. Let's say if I have a pair of conjugate poles. So suppose we have a pair of conjugate poles in the S domain. Okay, and then basically that means a transfer function, okay, more or less look like this. So this is a transfer function in the S domain, right? If you set the denominator to be 0, and you get your poles to be sigma plus minus j omega, right? And if you look at your Z table, you look at the Z table here, and you'll find that the inverse Laplace transform is basically e to the power sigma t sine omega t. So if you look at Z table, you'll find this relationship very handy. That's essentially sinusoidal curve, and then superimposed by an envelope, which is e to the power of a sigma t at here, right? Then you can do the similar work. Let it pass through a sampler. Okay, so the t changed to kt, and that's the digital basically signal, right? So here's continuous, here is discrete. Okay. And then you can take Z transform for this discrete sequence of signal here, and then you get, okay, if you can look at the table, and you get basically Z transform Gauss transform function you basically get this one here. Okay, so it's all in the table. Okay, now you can verify this again. So here on the left side here, you got two poles. Okay, sigma plus minus j omega. Then you can verify that. Okay, if you use this relationship, then what you get here is basically you get two complex poles, okay, for the basically Z transformation, okay, and these two here is e to the power of sigma t cosine omega t plus minus j sine omega t, okay, sine omega t, yeah. And that's essentially the same format as this is basically e to the power sigma t angle omega t. Right, or e to the power sigma t and then e to the power of j omega t. It's all the same writing, right? The same writing here. So you can verify yourself. Basically, what I'm trying to illustrate it here is the mapping of the poles, right, from S plane to Z plane when you're impulse sampling, okay, through this impulse sampling process. So whatever continuous signal, if you have an impulse sampler here and you get the discrete signal, right, so the shape of the discrete signal probably will maintain the inputs here. The poles, okay, so basically is transposed, is mapped through that relationship. Okay, so before we dive into all the mapping, detail mapping there, okay, and I wanted to cover one simple concept here basically. And that simple concept here is the natural frequency, okay, in continuous and discrete domain. Okay, so this is something. This is just basically a concept trying to let you get used to the idea of this natural frequency. In continuous system, this is quite simple. Let's say I have a sinusoidal curve written as sine omega nt, right? This is continuous, okay? And you can plot this basically. It's a sinusoidal curve with a frequency here omega n, right? Yeah. So omega n at here is basically what we call the natural frequency. Okay? So that's the frequency of the oscillation. Okay? Now, if we're going to sample this sinusoidal curve, okay, so let's say we sample that using a sampling time t. Okay, so we sample using a sampling time t. So your sinusoidal curve becomes this one here, and that's basically a sequence of numbers now, right? A sequence of numbers. Okay, and it really depends on this sampling time, the choice sampling time. Then you generate basically different sequence numbers, right? Yeah. If you pick your sampling time too big, then the numbers you generate may not be exactly the sinusoidal curve anymore, right? Yeah. But either way, you know, out of this one here, let's say we rewrite this into sine, okay, omega n t times k. Okay, let's rewrite it to sine omega n t times k. So you basically can imagine you get okay, a whole bunch of that's sort of the original basically, right? From strength. This is actually good sampling. You know, if you have a bad sampling, then you won't be able to even to plot out this sinusoidal curve here, right? Okay. So between, of course, we know that between each samples, okay, between two samples, you have a sampling time t there. Okay. So now, first concept is, okay, what's the total number of samples, okay, per period? okay, the total number of samples per period. So basically means, so here's one, for example, if you look at this one here, it goes up and it goes down and then back again, right? So that's basically called one period, right? One period. So within this one period, how many number samples here? So how do we calculate? So let's say we call it total number here. Let's call it capital N. Okay. So how we can calculate it? We use the period, right? How long, however long the period is. And the period is basically, here you have a natural frequency omega n here. So 2 pi over omega n, you get the period of the sinusoidal curve, right? Yeah. So this is total period from here to here, and divided by one interval. So divided by one interval here, that'll give you basically the total number of samples per period. Okay. So I can rewrite this one into 2 pi over omega n and divided by t. And 2 pi divided by capital T sampling time, which is basically omega s over omega n. So that's your sampling frequency over natural frequency omega n and here. Okay. Yeah. So now the idea is, okay, you have a sine omega n times t times k. Okay. Don't think this as a sinusoidal anymore. Okay, just think of this as a discrete sequence number now. Okay, this is basically a discrete signal number. So for this one here, this is a discrete signal, right? So I can see that this discrete signal, okay, it repeats, okay, every this many number of samples basically. Okay, so every n number of samples, that discrete signal will repeat itself, right? Yeah. So you can imagine this number of samples here. There's, in my case, draw 6 or 7, and then you repeat itself. Okay. Yeah. Now for the same signal here or number here. Okay. And mathematically, what we can do is, okay, so we can add a 2 pi. Okay, we can add a 2 pi at here. Okay, so whatever signs and degree, then you add a 2 pi. Basically, it's not changing, right? It's a periodic function. So then for the same signal, I can rewrite it as this. So that's be reading. So omega n times t. Take out this omega n times t, and then k at here, and then inside here becomes 2 pi over omega n t. Right. Okay. And if you look at this carefully here, so omega n here, that 2 pi over omega n t, which is what? Exactly this capital N here, right? That's your capital N. Okay. So essentially so let me put it down here. This discrete periodic discrete signal here, right, can be written like this. Okay, can be written like this. So you see that n essentially is like the period, right? It repeats every n number of samples here. Okay, so for discrete one, repeats every n number of samples. For continuous signal, your omega n is a natural frequency. So now if I look at the discrete signal, then the natural frequency should be what now? Should be this quantity. Okay, should be this quantity. So we let's say theta equal to omega nt. Okay, this is basically called the natural frequency. Okay, for this discrete signal. Okay, for the discrete signal here. Okay, and this is natural frequency basically in the Z domain now. Okay, it's a different. Previously took omega n, and now is omega nt. The unit for this natural frequency, okay, the unit for this one here, okay, is not reading per second anymore. So this is the reading per sample. Okay, it's the reading per sample, and I'll show you what does the reading per sample means. Okay, yeah, good. So let's take a look at an example here. Okay, and through the example, we'll have a pretty good idea of what natural frequency means in a digital domain. It's actually quite different. Okay, it's quite different. So let's use a sample signal here. This time I choose a sinusoid, a cosine here. Let's use cosine pi over 8 times t to illustrate this natural frequency concept here. Okay, yeah. So we're gonna sample this signal here, okay, and that give us discrete signals. Cosine pi over 8 times small k. K is a sequence, right? Times sampling time. So in this particular case, my omega n equal to pi over 8, right? In the continuous domain, your natural frequency is pi over 8. That's the frequency. And after sampling, you get this one here. So what we're going to do is I'm going to choose a different sampling time to illustrate. I'll use 1, 2, 4, and 8, okay, to illustrate the effect at here. So basically, when t equal to 1, what do you have? You have a cosine pi over 8 times k. And when t equal to 2, you have a cosine pi over 4 times 8, right? So pi over 8 times 2 give you pi over 4. And when t equal to 4, you have a cosine pi over 2 times k. And when t equal to 8, you got a pi over k. Okay? So that's really what happens when you pick a different, basically, sampling time here, right? Pick a different sampling time. Okay, so now here's a graph, basically based on a different sampling time at here. Okay. Okay, so here's a graph here. So let me copy this graph into my OneNote over here. Alright, so let's take a look at the graph here. So when you have a t equal to 1, and this is the sinusoidal, it definitely looks like sinusoidal, right? When t equal to 2, it still look like sinusoidal, but you have a less number of samples now per period. Okay. When t equal to 4, and you got this, right? When t equal to 8, and you got this. Okay. So apparently, when t equal to 8, that's such a big sampling time. You look at this one here, you can't actually see this is from a sinusoidal curve at all, right? Okay. Yeah. So my question to you is, okay, if you look at the 4 graphs that are here, which one has the highest frequency? The last one, right? Because why? Because you got up and downs, right? That's basically the last one. You have a highest frequency at it here. And according to my definition, you'll see here, my natural frequency definition for the discrete domain is omega nt. This is a natural frequency here. So if I look at the current example here, the natural frequency for the discrete domain, so basically the first one, this is natural frequency, right? This is natural frequency, this is natural frequency, and this is natural frequency. Okay? Yeah. Good. So now you can absolutely see the last one is highest frequency. So my second question to you is, can you get any other frequency that is higher than the last figure at here? Would you be able to still get a natural frequency that is higher than the last figure, than the one showing the last figure, this figure here? Can you? No. Right? You can't. Well, what's this one here? Up and down, right? You can't have any other faster frequency than that one here. Okay? And what's the natural frequency for this one here? Theta equal to pi. Right? Theta equal to pi. What's the continuous natural frequency? It's pi over 8 here, right? Pi over 8. Okay. So if I change the omega n to a different numbers, I can increase or decrease the natural frequency. I literally can have a negative infinite to positive infinite in time domain here, right? But in discrete domain, so now you see now, what's the fastest natural frequency? Theta equal to pi, right? So if you have a cosine pi k here, if you look at basically trigonometry, this is essentially equal to what? -1 to the power of k, right? -1 to the power of k. So, and I conform this when k alternate between the odd number and the even number, then it alternates between the positive and negative numbers right here, right? Yeah. So basically, the point at here is theta equal to pi, okay, or positive negative pi, okay, or negative pi. So theta equal to positive negative pi. This is the highest frequency, okay, of oscillation. Okay, so that's something that you need to basically set up in your mind and to differentiate the natural frequency concept between the continuous domain and the digital domain here. Okay, yeah. But you also have to be careful. Basically, of course, we have the cardinal rules. Basically, the Shannon theory, right? In terms of the sampling frequency choice. Okay, so this one here does have the fastest natural frequency, but you know, this is basically because of the very yield peaked sampling time, right? Yeah. Okay. Okay. So second of all, okay, if you look at another thing I wanted to back up here is, remember the sampling time? I said the unit is the readings per samples, right? So basically, every sample, how many basically readings does every sample cover? So if you look at the last one here, if this is pi, so this is supposed to be what? Pi reading per sample, right? So if you look at the way it goes, you have every time, so that when it goes up, down, then repeats. So basically this portion in here should be what? Should be 2 pi, right? That's one period. So one sample here cover pi readings per sample here, right? So that's basically what it means in here. Okay, yeah. So let me give you another example here, and just to illustrate this simple concept here. Okay, or to give some meanings to the numbers here. So I think I used this example when we cover the Z transformation. So here you have a pulse transfer function, for example, and you can set the numerator, okay, and then let it equal to 0. Set the denominator, let it equal to 0. Solve for the roots, and we can find that the roots is this one here, which is a pair of conjugate poles, okay, conjugate poles, and that you can always write it into this format, r angle theta, okay, r angle theta. So for this particular case, r angle theta give you 0.8 and then pi over 3, okay, pi over 3. Okay. So your discrete, if you do an inverse Z transform, and this is basically will give you 0.8 to the power of k times a certain constant here. You can take a look at the lecture notes. That's what the a is, and then 0.3 times k, and then plus a phase angle phi. Okay, phase angle phi. This is the discrete signal. So the capital A, capital phi here you can find in the lecture notes, okay? And in lecture 2 or 3. So in this particular case, you can see the natural frequency, which is what? Theta equal to pi over 3, right? So that's your natural frequency, omega nt. And then you can calculate how many number of samples per period. So use the formula, you get basically 2 pi over theta which you get to 6. So there are 6 number of samples per period. Okay, and because of the R at here is 0.8 less than 1, so we can for sure know that this signal will go to 0, right, as k goes to infinite. Okay, yeah. And here's a graph of this signal right here, so you can take a look at this. So this is a graph of the signal here. Okay, yeah. So then what it means, it basically goes up and down, right, and then start to repeat like this. So you can see 1, 2, 3, 4, 5, 6. So that's 6 samples per period, right? And for one, basically a period is 2 pi, okay? And if you divide it by 6, so you get basically for each sample it covers pi over 3 reading per second here, per sample here. Okay, yeah, that makes sense. Yeah. So that's basically sort of like a preamble here to give you some idea of what the mapping is and what does it mean by discrete signals, right? Yeah. Now, when we talk about the natural frequency or vibration of, based on the discrete signals here, sometimes it's completely unrelated to your continuous one here, right? Yeah. So, but however, right, if nobody really tells you where that sequence number is from, then you really don't know what really means, right? The connection there. So all you can do is just analyze based on this sequence number in the digital domain. Okay. Yeah. Okay. So now let's down to the actual topic here about the mapping here. Okay. So let's look at the mapping from S plane to the Z plane and here. Okay. So we'll look at a bigger picture in general, and then later we'll break it down to a lot of specific cases, okay, to talk about the mapping here. First of all, let's look at the general one here. Okay. Suppose we have, okay, let's say we have let's just use the one here. Let's say we have a complex pose, okay, in the S plane. And of course, we will be only interested in the left side of the S plane, because that's the stable plane, right? Stable side, and which means the real part of this S, okay, or the pose, needs to be less or equal to 0. Okay. Yeah. Now, mathematically, we're gonna do the mapping now using that relationship Z equal to e to the power Ts. We substitute the S into this equation, so e to the power of t times sigma plus j omega, and using simple algebra, you get e to the power sigma t and e to the power of omega t. So this Z here, basically this pole is mapped into the Z plane, which is this one here now, right? Okay, and for this particular one, this is your modular here, and this is your arguments. So, okay, that's the complex pose in the Z plane. Okay, so let's continue from this one here. Okay, let's continue from this one a little bit here. I'm not going to touch the modulus part or the magnitude, but I will add, okay, a 2 pi k at here. So this is angle basically, right? This is sine omega t plus j sine omega t. So if you add any integer number of this, multiple of this 2 pi to the theta, so sine, cosine, they don't change. Okay, yeah. Then one more simple manipulation. Take out this capital T out. Okay, so we get omega plus 2 pi over t times k. K is any integer, so k equal to 0, 1, 2, okay, like this. And it can actually be negative numbers, okay? It can be negative numbers. Positive 1, positive, let's put it this way here, okay? Yeah. Okay, so what does this tell us here? Okay, one more step here. And that 2 pi over omega t is omega s. It's a sampling frequency. Okay, sampling frequency here. So what does this expression tell us then, right? So I'm gonna illustrate through the graph here. Okay, so suppose this is the z plane here, and this is the imaginary axis. This is a real axis, of course. Okay, yeah. So if you look at basically the expression over here, right? Look at the expression here. So the expression has a real part, which is a sigma. So for example, basically, sorry, this is not a z plane. This is s plane here. Okay, this is s plane. Okay, yeah. So you have a sigma here. Let's say this is the sigma. Okay, this is sigma here. And you have also omega here, right? So let's just say omega is over here. So this is omega. And this is the original, basically the original location of the poles, right? Okay. So then what do we do now? If you look at this, if I just do the mapping here, so this is e to the power sigma, so this mapping here, and I can basically say, okay, so let's do the mapping now, right? Let's do the mapping. And here is the z plane. Okay, this is imaginary. This is the real part, right? Imagine the real part. And after the mapping, what do you get? You get this. You get this quantity and this quantity here, right? Yeah. So e to the power sigma t, because sigma is less than 0. So e to the power of any negative number, you get a less than 1, right? Yeah. So basically, this number here will be mapped to, okay, somewhere. Let's just say somewhere over here. Okay, right? And corresponding to a certain angle, omega t at here, right? Omega t. Okay. So that angle, this is the angle here, omega t, right? And this is the r at here, right? So that's this point, this pole here is mapped to here, and we for sure knows that, okay, this is going to be within a unit circle, right? For sure we know that. Okay, so that's a mapping. However, mathematically, right? So I went over a few more steps here. Mathematically, from here we can come over here, right? Come over here. Now from here to here, it mathematically is equivalent, right? It's equivalent. But physically, what does it mean? So see, this is mathematical means from here is equivalent. Physically means originally you have a sigma and omega, and now you have a sigma and what? Omega plus this one here, right? So sigma not changing, so this is not going to change. You have omega here. So let's say k equal to 1 or negative 1, which means omega plus omega s. So let's say this is this location, and this location is omega plus omega s, right? And then you can go, if k is negative 1, so you can, let's say here, this is omega minus omega s. So now you're here, right? And you can keep changing the k from 1 to 2, so that's probably over here now, omega plus 2 omega s, okay? And then here's omega minus 2 omega s. Okay. So now you see all of this, right? All of the additional ones. So this is the big red dot is the original. But mathematically, all of the other black ones, they're literally all going to be mapped to where now? To the same location, right? Okay, it's the same location here. Okay. So what this tells us is, number one, well, actually no number one, just only one here. Okay. So what this basically means is, if you are given a pole, okay, in Z plane, okay, if you're given a pole in the Z plane right here, it literally means there are infinite number of poles, okay, in the S plane. Okay, to map to. So that basically an idea, tell you, if I have a pole in the Z plane, I can actually have an infinite number of poles in the S plane to do that, okay, to map to over here. Okay. And of course, if you have a one pole in the S plane, that will map to one location in the Z plane, okay, but not the other way around, essentially. Okay. Yeah. So the other thing that you need to observe it here is there are infinite number, and all of these poles that are here, they are separated by omega s in this along the imaginary axis that are here. Okay, yeah, it's not arbitrary. It has to be separated by omega s that are here. Okay. So that brings naturally to the basically the next question in here, right? Since there's so many, basically there's so many here, so it's like a repeating, basically, right? It's like a repeating. So the next question here is basically, we probably don't really need to look at all of these poles that are here. So that gives us the concept of so-called primary strip and complementary strip. Okay, yeah, primary strip and complementary strip. So let me show you what that means here in terms of the primary strip and complementary strip here. Okay, yeah. So I'm going to draw in S plane first of all. Okay, in S plane here, imaginary axis and real axis. Okay, so I don't really need this long in here. All right, so I'm going to separate this S plane, because this is S plane. I'm going to separate this S plane into different, to strip it into different regions. Okay, the first region we're going to separate that is this. So let's say you start from the D location here, and then the D goes all the way back to this A location, and A location in here is negative J omega S over 2, and then it goes up over here. Let's call this B location. That's J omega S over 2, and then it goes out until the E location in here. Okay. And that's one basically strip. And as you can observe, the variation from A to B is from what? From negative J omega S over 2 to J omega S over 2, right? And so the interval from A to B is how many absolute values? What is omega S, right? It's omega S, and that's basically the idea over here. From here to here, one interval, omega S, right? Omega S here. Okay. Yeah. So this region here, I'll show you the mapping here. So this region in here is called the primary strip. So this is called primary strip right here. Okay. Yeah. And then you can basically go up and down, okay, based on the primary strip. Let's say if I go down here, I'm going to go down up to negative J 3 over 2 omega S. If I go up, then I'll go to J 3 over 2 omega S. Okay. So you can go up and down by an interval of another omega S. Then you can construct basically as many as possible, right? Up and downs. And those region here, so they're called complementary region here. So they're called complementary strip. Right, complementary strip. So we'll focus only on the primary strip, and then I'll show you why we can only just focus on the primary strip here, right? So let's do a little bit of mapping at here, exercise. I'm going to map this primary strip region to the Z plane at here. Okay, so let's take a look at how that mapping gonna happen. Okay. So again, we're gonna assuming this S equal to sigma plus G omega, right? So this S plus G sigma plus G omega, it's somewhere within this primary strip, okay, within the primary strip. So I will actually only look at the boundaries, because the boundaries, mapping the boundaries, will basically give us the bigger picture, the overall, like this, right? Okay. Yeah. So first of all, let's think about the D location, this D location here, right? Yeah. So for the D location, it's literally basically means it's set infinitely on the left side of the S plane, okay? Infinitely to the left, which means the sigma value for the D is negative infinite, right? Negative infinite. And that, when you have S equal to sigma plus G omega, remember what does the mapping now? It's e to the power of sigma t and e to the power of G omega t, right? That's the mapping. You know, you substitute into z equal to e to the power st. Okay. So now you see, if sigma is negative infinite, so that basically means your R, this is the R here, right? Your R equal to sigma t will be approximately what? Huh? Negative infinite, the R approximately 0, right? 0. Okay. And the D here corresponding to negative G omega S over 2 value here. So D corresponding to this, and then basically when you have omega equal to omega S over T, and there's a negative. Okay. When you omega equal to negative omega S over T, so you substitute into this omega T, which is theta, right? Which is theta here. So substituting in this one here. So omega S over 2 substitute into here, and capital T equal to 2 pi over omega S. Okay. So what do you think this theta value is when you substitute negative omega S over 2 into here? What do you think the theta value is? Remember T, huh? T equal to 2 pi over omega S. So this negative value times this one here, and theta equal to negative pi, right? Equal to negative pi. Okay. So your D point, okay, which is on the infinite left side here, will be mapped to which location in the Z plane? R equal to approximately 0, okay, approximately 0. And theta equal to approximately, not approximately, theta to exactly negative pi. So R is approximately 0. It's got to be somewhere very close to the origin, right? If really this is infinite, then that's 0. Okay? But you want to differentiate this a little bit here. So it basically, you get let's consider not a 0. Let's say R is not a 0, R is 1 or something, right? If R is 1 and theta is negative pi, and how would you draw that vector or complex number? It's basically somewhere here, right? Somewhere here. But now you're gonna basically from here go all the way as close as possible to the origin, isn't it, right? Yeah. So you basically you have a D point, okay, somewhere down here, okay, below that horizontal axis. Is that okay? Right. So because you got a negative pi here. Negative pi meaning from here to here is negative pi, right? This is negative pi, okay? Yeah. Okay. So if like if you have a vector here, you know, this is a negative, this theta is negative angle. This is the magnitude. You can imagine to the extreme type of situation, this vector will go smaller, and the angle will go to negative pi, right? So that's how you can figure out the actual basically D locations. So D locations it's here, okay, but it's a negative pi, okay? Yeah. So now let's take a look at the D location. Now let's move the D all the way to A location, right? Move the D to all the way to A location here. So what about the A location? Okay. For the A location in the S plane, and how is that going to go? So for A location, A is on the imaginary axis. So your sigma equal to what? The real part for the A location, sigma equal to 0, right? Because the real part is 0. So then your Z, okay, will just equal to e to the power of j omega t, and j at here is omega s over 2 times t, okay, a negative, okay. So that gives you e to the power of a negative pi t, e to the power of negative j pi, right? Pi, okay. Because e to the power of 0 is 1, right? So is 1 here. So which means, where is my A location? If I draw it, the A location at here will be mapped to where now? So to the location. If this is negative 1 at here, okay, then A will be right here, right? Will be right here. So I can explode this a little bit here. Basically, the D, right, as it's moving from D to A over here, you are moving from here to here. Is that okay? Yeah. So basically moving along this 0 to 1, negative 1 here. So essentially the mapping for this part here, like from D to A corresponding to 0, 0 to negative 1, 0. Right? So that's the moving from here to here. Okay. So let's keep moving now from moving A to B, right? If we move from A to B, then for the B location, same thing, but B location is positive omega s over 2 times t e to the power of j pi. Okay, and this essentially in the z plane, it's still z negative 0, 1. Okay, because cosine pi is also negative 1. But right, sorry, what is it? In a second here. Yes, that's right. Yeah. So as you're moving from A to B at here, also try to imagine this other scenarios. Basically, let's say if you have a point somewhere here, and same thing from moving from here to here, or moving from here to here, right? Yeah. Instead of just purely moving along the imaginary axis at here. Because if I look at this currently, because I restrict the theta, sigma is all 0 at here, right? Yeah. So if a sigma is not 0, let's say if we're moving from here to here, what could happen is basically the location from A. So the location the B, first of all, location the B here is same location as A, except if you want to be rigorous, the B is actually on the top of A here because it's a pi, right? It's not negative pi. Okay, so A is negative pi, but B is positive pi. Okay, so as you're moving from A to B or somewhere within the region from A to B, then what's really happening, okay, is circle, exactly. So it goes all the way from here to here, right? Yeah. And this circle is along this unit circle, right? Along the unit circle here, okay? And you're keeping basically r equal to 1, right? R equal to 1, and it's moving from A to B, okay? So finally, moving from B to E, right? B to E here. So you can actually probably figure out now for E location, okay, your sigma is negative infinite, okay, negative infinite at here, and then you get basically R is approximately 0, and theta is omega s over 2 times t, which is a pi, right? So that basically get from B all the way back over the origin and here. So that's your E location, right? E location. Okay. So that's how that primary strip is mapped into the z-plane. Essentially, the boundary of this primary strip, okay, is this unit circle here, and then plus of the imaginary part, D to A and E to B to E, corresponding to this part at here, right? Corresponding to this part. And if you do a mapping for the complementary strips, okay, do a mapping for complementary strips, and you can imagine, all you're gonna get is what? It just keeps moving around this circle here, right? Keeps moving around. Okay? It's always from basically negative pi to positive pi at here, right? Yeah. So that's why we'll focus on basically now only on the primary strip, which is from here to here, right? And then it goes around. Okay. Yeah. Is that good? Okay. Now, before we move on here, just reinforce here. Remember the natural frequency, right? Natural frequency. What is the maximum natural frequency in the digital domain? Theta equal to negative positive pi, right? So if you look at the z-plane at here, if I wanted to ask you which region corresponding to a high frequency region, which region corresponding to a low frequency region. So if you look at this one here, which region would be a high frequency region? The region got to be the region around what? Theta equal to positive and negative pi, right? Where is the theta equal to positive negative pi? Here. Okay? So this region, right, is close to positive negative pi, right? Which basically means if you have a pole in the z-plane that's close to this region, and it doesn't matter, it doesn't have to be exactly on the unit circle. It can be anywhere here, right? But as long as it's like a reader covered by that region, then you should expect that pole will result in a higher frequency, okay, in the response, right? And where will be the low rate frequency now? It will be where? It will be over here, right? So over here. So this is low frequency, and this will be the high frequency region, okay? Okay. Any questions so far? Okay. Good. Okay. Now, again, there's one more thing I want to cover before we start to talk about the mapping here is, so we're recycling the knowledge from continuous system, okay? So we have to basically know very well in terms of the system response in a continuous domain, right? So this is where I'm going to have to spend a little bit of time to quickly review response of a typical second order system, okay? The Laplace transfer function for a second order system, okay, which is written like this, okay, it's written in the natural frequency and the damping ratio parameters. Okay, yeah. Now, why am I just sort of focusing on the second order system? Right? That is because if you recall, when you have a continuous system, in a time domain, right, and second order system is a very useful transfer function, because a lot of the time your closed loop Laplace transfer function, okay, even though it's not second order, maybe you have a third order or fourth order, okay, the high order system could very well be modeled as a second order system. Some of the poles that's probably very far away from the imaginary axis, then basically means you have a fast decay because of the pole, so that doesn't really play much of an effect into the system response. So that's why second order system is well studied, because it's a good approximation even for high order ones. Okay, yeah. When you have a second order system, let's assuming you have we're assuming gonna have a complex poles here, and you can rewrite, okay, the denominator, okay, into this expression. So no change, just rewrite it. Okay, yeah. And furthermore, this can be rewritten into this one here. Okay, so this can be further rewritten as this equation here. So no change, because just basically if you cancel all the common terms here, you'll see there's no changing anything here. Right? Yeah. But what I wanted to show at here, basically, if your h of s is written in terms of this one here, and you can do an inverse Laplace transformation, then you get your time function. Okay, you get your time function, which is omega n over square root 1 minus zeta square e to the power of zeta omega nt and sine omega 1 minus zeta square times t. So that's the inverse Laplace transfer. That's a time response, okay, based on this second order transfer function. Okay. So for this particular one and here, basically if you relate to the Laplace, essentially you get you have two complex conjugate poles. So negative zeta omega n plus minus omega n square root 1 minus zeta square. Okay, so you have and then plus multiplied by j. Right, that's a complex conjugate poles here. Real part is this. Imaginary part, we call that omega d. Okay, so real part, imaginary part. Again, zeta here is damping ratio. Omega n at here, natural frequency. And omega d at here, if you recall that, what does omega d called again? Anybody? That's right, it's damped natural frequency. Okay, yeah. And if you plot this ht here, this essentially you got a sort of a constant gains at here. Then you have a exponential decay function. Then you have a sinusoidal function at here, right? Yeah. So you multiplying all of this together, and if you plot this h of t, so h of t very well will be look like this here, okay? And it's bounded by, okay, it's bounded by two envelopes. The top envelope is omega n over 1 minus zeta square square root e to the power of this. Okay? And bottom here is just put a negative sign. Right? So that's basically in the continuous domain here. Okay, in the continuous domain. Okay. Yeah, we can talk about this later here. Okay. So if this is the pulse trans function, let's say if this is your closed loop, okay, a pulse trans function, and you can give any input, right, to this h of t here, okay, to the h of t. We typically use, let's see, step response, okay, to analyze the system performance. For this kind of system, you can apply a unit step input, okay, then your response, okay, could be something like this, right? Yeah. So based on the step response, we have a number of very important parameters, right, for system design essentially. Okay, number one, okay, so number one in here called settling time, and we call TS at here. So settling time basically means how long it takes to settle within a certain percentage of the steady state value here, right? So this is steady state. So how long does it take to settle within, let's say now we have either 1% or 2%. Okay, so there are two different criteria for settling time. You can have 1% of settling time. So how long does it take to settle into that 1% region? And this is the results. Okay, when you have a second order system, okay, and it takes, okay, roughly this much time to settle into that region, right? If we're talking about 2%, then the TS, okay, will be zeta omega n 4 over zeta omega n. So slightly smaller, of course, right? It takes a little bit faster, basically. Okay, that's the first one here, and then the next one is called the percentage overshoot. Okay, the percentage overshoot, and that parameter is called MP. So percentage overshoot, basically you look at okay, here. So here is the maximum number overshoot here, and then you use this much divided by the steady state value, then you get the percentage overshoot, right? Yeah. The zeta ratio, basically the damping ratio, determines the percentage overshoot. But the connection between this MP and the zeta value, okay, is given as e to the power negative pi zeta over 1 minus zeta squared. Okay. And that's the percentage overshoot. And then you time 100%, so you get percentage overshoot. So based on this formula, you can inversely, if you're given the percentage overshoot, you can calculate what's supposed to be this damping ratio, right? So that inverse formula is this one. Okay, that's this one. So that's damping ratio. Okay. And some of the very common relationship is if your MP is 16%, and that corresponding to zeta is approximately 0.5. If you're looking for a 5%, and the zeta should be approximately 0.7, right? Yeah. So the bigger zeta, the less overshoot for sure. That's the second important parameter, percentage overshoot. And when you design in continuous domain, those are basically the specifications that you rely on or you use, right, to design your controller. And one more is the so-called the peak time. Okay, so basically, how long does it take to reach the peak? So this is the peak here. So this is basically give you this the peak time, capital TP. The formula for TP is pi over omega d. Omega d is a damped natural frequency. Okay. So that's how you can get roughly this peak time based on the second order system. And also the idea of this, another one is called the time constant. Okay. Tau. Time constant tau in this second order system is approximate. This is approximate. Okay, this is approximately 1 over zeta omega n. That concept basically, how long does it take to reach 63% of the steady state value, right? And that's your time constant tau. Okay. And the last one we wanted to use is the so-called the bandwidth. Okay. The bandwidth, the BW, and the rise time. Call it TR. So small tr. TR is approximately 1.8 over Wn. Okay. So rise time refer to the time it takes to reach 90% of the steady state value. And then the bandwidth of the system is approximately 0.35 over TR. Okay, the TR here. So bandwidths are typically referred to, how much of a frequency bandwidth that has a meaningful frequency bandwidth of the system, right? Normally up to -3 dB. And if you have a further higher frequency, then there's going to be a drop, further attenuation, which will basically generate no meaningful response. Okay. So this is, let's say, the -3 dB over here. So that is the bandwidth, right? It's the bandwidth here. Okay. So we're gonna make use of, essentially when you start a design, your initial steps always in a continuous time. Okay. So the user really not going to give you the discrete requirement. The user will give you, okay, in the continuous time, what's my requirement, right? My requirement is certain percentage overshoot, certain settling time, or certain time constants, right? That's the idea. Okay. So those are your starting point. Those are very important, basically, very important parameters that you will rely on, right, to calculate things. Okay. Here's a quick example over here. Let's see. Okay. So suppose that we were given settling time. So let's say we're giving a settling time Ts at here. So when you're giving a settling time Ts, this kind of concept here typically meaning at least, right? Because you probably want to see, okay, at the most, that doesn't make sense. So at least you want to reach the steady state region 1% or 2% within a certain amount of time. Okay. Yeah. So suppose we are using the 1% in this case. Right. That's the 1% formula. Here's your sampling time formula. If Ts is given, right? If Ts is given, then we can solve something for the right side here, right? Yeah. Now the bottom here is zeta omega n here, zeta omega n. Now if you look at my notation wise, when you have a second order system, what is the root? The root has a real part, which is what? Negative zeta omega n, right? That's the root of a second order system. So basically means if you're given settling time, okay, your Ts So you can, I'll just put a negative sigma here, right? Because sigma equal to negative zeta omega n. Then we can solve for the zeta at here, right? Solve for the zeta. Okay, solve for zeta. Negative. Okay, yeah. So you can, if you're given Ts, you can solve for zeta. And what does the zeta basically mean? Let's say, based on this simple calculation, you find, okay, so zeta equal to here, not zeta, sigma equal to this much, right? Sigma equal to this much. So let's say you find sigma, I don't know, sigma equal to -2 or whatever, right? Okay, yeah. Sigma is over here. Okay. Now remember, the Ts is at least, right? So at least this much at here. So that means the sigma here, you solve for this, you get a boundary here. So that means what? The sigma needs to be at least, so it needs to be less than or equal to this number here, right? This number here. Okay. So if you're gonna design for a system, here is your root, right? Here's the your root at here. You're gonna pick a sigma, right? You're gonna pick a sigma to satisfy the settling time Ts. So where would you pick the sigma? So you see, sigma needs to be less than this, right? So basically means you can draw a vertical lines at here. Okay, you can draw vertical lines. Then any number, right? Any points on the left side of this vertical line will give you a sigma that is less than this much at here. Okay. So if this is the only requirement, then you literally can see, okay, I'm going to pick a point in here, right, as my my pose for the system. That makes sense, right? Yeah. That's basically how you can figure out a pose in a continuous domain based. This is a simple example based on a given based on the given requirements, right? Requirement. Okay. Yeah. Now, how is that? Further a little bit here. If I have a second order system, okay, which is this, what I'm written at here, which is a second order system in here, and I'm going to do the mapping now. I'm going to map this one here, right? Map this into the Z plane, okay, in the Z plane. Then let's take a look at the results of the mapping at here, right? We use Z to the equal to e to the power st for the mapping, okay, and in this case my s value equal to, right, that's the root of the second order system. Then I'm going to substitute s into this equation in here, so z equal to e to the power negative omega nt, so this is the real part, right? And then e to the power positive negative, okay, so there's a positive negative here, and then j times omega n 1 minus this guy times t. Okay, so that's after mapping you get this, and this one equal to r angle positive negative theta. Okay, yeah. So r at here equal to e to the power of z to omega nt, and theta at here equal to omega n 1 minus zeta square root times t, okay, or omega dt, right? Omega dt. Okay. Okay, good. So you see this information at here, what it trying to establish is now is, remember the mapping here is basically this is from continuous S to Z at here, right? Yeah. But ultimately, at the end of the day, what you're gonna get is not an S plane. What you're gonna give is, here's a Z plane pose, right? You're gonna pick a Z plane pose basically, okay? Or in other words, you're gonna end up with a R or theta value, right? And then you have to ask yourself, given r theta, what type of response does it correspond to, right? Or basically, what type, what's the value of percentage overshoot? What's the settling time? Or what's this? What's that? What's that? Okay, yeah. So the ultimate at the end of the day is you're gonna look at is given r and theta, right? We try to calculate what is this zeta, what is the omega n at here, okay, corresponding to the time. So here you have r, you have a theta. Based on these two equations here, we can calculate our zeta to be ln r negative ln r over square root ln r square plus theta square. And omega n can be calculated to be this much. Okay. This is very important. So because I think if you recall, when I teach you the pole placement, there was an example that we went over in the pole placement, right? Basically, we started with a certain pose and we're not satisfied, right? And then we wanted to place the pole to somewhere else, and that new location of the poles are based on certain requirements, right? And that basically new location poses meaning new r, new theta, right? Based on a certain criteria of zeta omega. So that is exactly the formula that we used in that example there. Okay? Yeah. So this equation and here are used for essentially, if I give you a pole, let's say 0.5 plus negative 0.5 here, z equal to this. Here is the pole I'm going to place in the z plane. It's okay, right? Yeah. Then the question here is, what does these two poles do to us, right? So you can substitute r and theta over here. You get a damping ratio, you get natural frequency. Okay. Then you roughly know, okay, so this is actually what it really looks like, what approximately will look like in a continuous domain, basically. Okay. Yeah. So that's the point. But of course, we're going to look at we're having more details here, right? But the bigger picture, this is essentially the biggest picture you could have here. Okay. I think I'm going to stop over here, and in the next lecture we're going to look at I'll go one more example, and then we're going to look at all the specific mapping examples from S to the Z. Okay.